the universe undoubtedly extended, empowering out and out more first-rate length. After this period, it persevered to develop, however at a more languid expense. In the changing over into the universe we concentrate on as of late, that is the inflationary hypothesis of the collectible cosmic impact, the most prominent and generally saw speculation of how the universe began. Anyway, for a couple of physicists, this head theory does no longer precisely painting the develop of our universe. Recommended, the universe existed before that thing, stretching out endlessly into the past as well as into the future. Even as the universe is expanding these days, it became contracting ahead of time than the enormous detonation. In this view, the enormous detonation isn't really a bang, as a jump, a second. Even while the contracting universe exchanged ways and headed out to make once more, as laid out through their hypothesis, the universe might have to sidestep with proceeded with improvement, less dissuaded by a breakdown inside the some distance future. Then another leap, a few physicists proposed the S may be endless. This horrible circumstance, the standard cosmological view in which the entire matter originated with a huge bang. The first-class physicist Brian Cox's also difficult circumstances, the hypothesis of how things arrive to advance, that something can't rise out of nothing, adding to the stress. The James Webb Telescope has made alarming disclosures conflicting with the idea that the enormous detonation might be thought about the start of the universe. These discoveries convey up the inquiry, if the huge explosion wasn't the start of the universe, then what was? Should the universe in the long run start with a detour or something most certainly unmistakable? The idea that the universe had a start or an evening with no yesterday as it became originally analyzed gets back to George Lamra in 1927. Simultaneously, it's far a less than ideal circumstance to show that the universe probably had a start. That length of cos history has barely anything to do with the hot broad bang that portrayed our basic universe. However, exceptional area subject matter experts or even a minority of experts, regardless of the reality that live with conviction that the enormous bang denotes the earliest reference point of all that all matters considered the definition is out of the enormous explosion isn't the introduction of life as we may be mindful of these days. In truth, there may be a ton of proof highlighted a non-singular start of our universe. We never showed up at those ends dependent generally upon no prominent endo or over-the-top temperatures. Our universe is great characterized by means of an inflationary length that occurred previously. The enormous explosion. The enormous detonation is the stop final result of what passed off inside the bearing of the culmination of progress. During improvement, the universe altered into most certainly void, no garbage, independent of no photons, just void region. Space itself became loaded with a gigantic amount of strength at each spot. This power changed after some time, reaching out in a fast and resolved design. Because the universe delayed, those adjustments relaxed to monstrous augmentations, while new bound-scale adjustments have been made to zenith. This superposition of insecurities all through scales is a portraying component of cosmological expansion. It's for inconsistent reasons, not purpose. If you lived in an expanding universe, you may potentially find close by locals where an expansion arrived at an end, or the region among you and them delayed persistently. In short, you could attempt to acquire what takes place nearer to the start of a huge effect before that area disappeared practically from view. It incorporates a little neighborhood, local taking all things together probability, no more prominent standard size than a human incredible hamster ball. Anyway, probably impressively bigger, the power capability of area then at that point gets changed over into be counted furthermore radiation. This change happens quickly, taking structure rapidly, yet not prompt. Because the energy shut up itself changes over into flume and some photons and more, the temperature rapidly expands from only a couple of degrees above outright Z to maybe around 20 Kelvin throughout the indistinguishable fast time period. Due to the enormous level of energy adjusted, all that activity is near the speed of gentle. All particles go about as radiation with colossal strength, whether massless or gigantic. This change is called warming, denoting the finish of progress, furthermore, the beginning of the degree, alluded to as the new enormous bang. As progress continues, you'll witness a colossal substitute from all past circumstances while the current enormous detonation starts. The expanding universe fast dials back after the secret picture of progress in an inflationary universe spot expands absolute illy with more prominent and expanded. Way away, regions, strolling ceaselessly, even as progress closes, and the new enormous bang gets going. Advanced more, farther areas will subside from you to an always developing certificate, it continuously as time advances. The piece of the universe in which improvement closes sees the augmentation cost drop, while the expanding regions surrounding it see no such drop. Under augmentation, the space to any object should twofold after a particular length, and while that equivalent measure of time slips by, that distance duplicates once more. Endlessly, once the huge explosion begins, this alteration since the expanding universe eases back down after the underlying second of improvement. Before the enormous detonation, you may experience improvement clearing off with adjoining regions. Those areas where in improvement closures will load up with antimatter and radiation and make greater more slowly than the as yet creating locals. Leaving you in the expanding neighborhood as a standard organization within spacetime, those areas in which intensity enormous bangs get up rise as far away from elite places, where improvement keeps. Because of this, they'll expediently subside from one another's view within the standard inflationary picture. Because of this, the improvement charge changes. There may be a little gamble that any universes with separate warm huge bangs will of all time cooperate. The area where we come to live gets rather fortunate and improvement arrives at an end for us. The power normal for space itself gets changed over to an intensity thick and nearly uniform expanses of particles, with the number 1 blemish and furthermore takeoffs from consistency. Concerning the quantum changes that existed and were relaxed across the universe, faster or later of advancement. The high-quality energy quantum fluctuations compare at first to overdense regions, while the awful energy fluctuations get converted into most importantly under regions. Those include as the seeds of huge structures. We can't see those thickness fluctuations lately, as they had been even as the universe most importantly went by means of the intense broad bang. There are not any noticeable engravings we can get admission to from that early span. Subsequent to going through extra affiliations, in spite of the fact that we can extrapolate back to figure out the underlying thickness vacillations, tracking down something consistent with the story of cosmic improvement. The temperature vacillations are engraved inside the inestimable microwave record, CMB, presenting proof of how the enormous detonation began. Yet there are different irregularities. Most of the CMB and our cutting-edge form of cosmology. We're missing something, and individuals can be summed up in 4 irregularities. First, on chiefly tremendous scales, the universe isn't generally acting as anticipated. The light from the CMB is being lensed by means of our Among Us and the CMB. That means the depend behaves like an enormous focal point, bending and changing over the plentifulness of the gentle in the return of it. The volume of this lensing isn't continuously predictable with our bleeding edge model, addressing a high-quality mission for custology. Besides, the different sides of the equator of the CMB sky have one-afaned normal temperatures, clashing with the assumption for consistency inside the universe's earliest degree. The possibility that the universe should have begun dependably results in various irregularities. Third, the expense of the Hubble consistent, which depicts how fast the universe is expanding, changes contingent on whether we degree it from the astronomical microwave noteworthy past CMBB or from neighboring stars. All in all, those abnormalities propose we are inadequate with regards to something fundamental by the way we decipher the universe. One proposed arrangement comes from circle quantum cosmology, which starts from circle quantum gravity on the structure of life in circle quantum cosmology. There's a littlest size of spot, the Board scale, or 1.0 x 10^35. This approach implies the enormous bang couldn't exist in a universe depicted through this rule. As an alternative, the universe should by no means come to a limitlessly little dense issue, close to the huge explosion. In circle quantum cosmology, while the universe became tiny quantum rectifications, and anticipated a frightful strain causing a leap on the other hand of a peculiarity. This shows that our universe might have begun from a first universe that contracted after which broadened all over again, similar to a phoenix rising from the cinders. While the idea of an enormous skip isn't absolutely new, all the time circle quantum cosmology gives a numerical structure to help its cyclic time. Very much like the possibility of an enormous jump, it is moreover situated in Who cosmology, including in a similar manner to this thought. If circle quantum cosmology is right, the early universe may have had a gentle energy and thickness. This current circumstance ought to alter the CMBB, showing up as gentle varieties in temperature all through the sky. These varieties measured through the quality energy range offer enormous proof of the universe's establishment, further guiding the chance of a leap ordinary. Circle quantum cosmology offers a convincing and open door to the ultramodern huge explosion variant, possibly settling a portion of the drawn-out status irregularities in cosmology and providing bits of knowledge into the beginnings of the universe. It besides gives a promising reason for the third an anomaly, the disparity in normal temperatures among the two halves of the globe of the CMB sky. The design gave with the guide of the method of circle quantum cosmology tends to the fundamental oddities situated in the CMB, the surprising way of behaving at huge scopes, and the lensing effect. In sync with Dr. Vetko of the Public Organization of High-Level Examinations, the open door that those anomalies are not simply length blunders but start from quantum gravity results right off the bat in the universe is a remarkable thought. That the universe started out in a vast leap has been proposed previously, yet its insistence requires further exploration. Vast fluctuation represents an endeavor in this view, as our perceptions might be restricted to specific parts of the universe, confounding our insight. Specialist Dwayne Johnson, a coist of a giant look at and a professor at 10RM College, highlights the difficulty in approving such speculations because of the large scale. However, the incorporation of late open doors like circle quantum cosmology and its ramifications protects the promise in settling novel cosmological issues. Notwithstanding these updates, a gigantic inquiry remains. Did the universe have a start by any means? Defenders of the universe having a beginning demand that it did. However, this brings up issues about the nature of the occasion that started out everything. On the other hand, cyclic cosmology suggests an everlasting universe, constantly present approach. Grandiose bobs. However, physicist William Kenny of the school at Bison recognizes the fundamental blemish in this idea. Entropy, the level of disorder in a system, increases with each cycle. In cyclic cosmology, this increase implies a beginning to a Big Bang conflicting with the notion of an eternal universe. The universe has expanded indisputably over time, a process observed and studied extensively. Initially, it expanded at an accelerating rate during what is known as the inflationary period. This phase, according to the inflationary hypothesis, occurred prior to what we commonly refer to as the Big Bang. The inflationary period saw the universe expanding exponentially, filling space with immense energy uniformly distributed. As the universe expanded, this energy gradually transformed into matter, radiation, and eventually the fundamental particles we observe today. The transition from a state of intense energy to one of material substance marked the end of the inflationary phase and the beginning of what we recognize as the hot Big Bang. This event wasn't a simple bang but a complex transition where the expanding universe started to cool and matter began to form. Contrary to earlier beliefs that the Big Bang was the absolute beginning of everything, modern cosmological theories suggest a more nuanced view. Some physicists propose that the universe existed before the Big Bang, perhaps in a contracting phase. This challenges the notion of a singular beginning and instead posits a cyclical or eternal nature for the universe. The concept of an eternal universe, where cycles of expansion and contraction repeat indefinitely, has been explored in theories like cyclic cosmology or variations of quantum cosmology. These theories suggest that the universe goes through phases of contraction and expansion, with each cycle potentially leading to a new Big Bang event. This perspective allows for the possibility that our current universe is just one phase in a series of cosmic cycles. Moreover, recent astronomical observations have raised questions about the traditional understanding of the Big Bang. Anomalies in the cosmic microwave background, CMB, radiation, and the distribution of galaxies suggest complexities that challenge the simple narrative of a single explosive origin. These anomalies include unexpected temperature fluctuations in the CMB and inconsistencies in the distribution of matter on large scales. The search for answers to these anomalies has spurred the development of alternative theories, such as loop quantum cosmology, which attempts to merge quantum mechanics and general relativity to describe the universe's earliest moments. This approach introduces the concept of a minimum size of space beyond which traditional notions of beginning or end may not apply in the conventional sense. In conclusion, while the Big Bang theory remains the prevailing explanation for the universe's origins, scientific inquiry continues to evolve. New theories and observations challenge our understanding and may lead to a more comprehensive framework that incorporates the complexities of cosmic evolution. Whether the universe had a definitive beginning or has existed indefinitely is a profound question that continues to drive exploration and discovery in cosmology. The universe, as we understand it today, is a vast and complex entity that has intrigued scientists, philosophers, and theologians for centuries. At the heart of our understanding lies the concept of the Big Bang, an event that is widely accepted as the starting point of our universe's expansion. However, the story of cosmic origins is far from settled, and recent developments in cosmology have challenged and expanded our views on how the universe began and what lies beyond. The Big Bang theory emerged in the early 20th century as a culmination of several key observations and theoretical advancements in physics and astronomy. One of the earliest proponents of the idea was Georges Lemaitre, a Belgian physicist and Catholic priest, who proposed in 1927 that the universe began as a primeval atom that expanded from a single point. This concept gained further support with the discovery of the cosmic microwave background radiation, CMB, in 1964, which provided strong evidence for a hot, dense phase in the early universe. According to the Big Bang theory, the universe began approximately 13.8 billion years ago in an extremely hot and dense state. In a fraction of a second, the universe underwent a rapid expansion known as cosmic inflation, during which space itself expanded faster than the speed of light. This inflationary period, proposed by physicist Alan Guth in the 1980s, helped to explain several puzzling aspects of the universe, such as its large-scale uniformity and the absence of certain relics predicted by earlier theories. As the universe continued to expand and cool, particles such as protons, neutrons, and electrons began to form. In the first few minutes after the Big Bang, nuclear reactions synthesized light elements like hydrogen, helium, and lithium. This period, known as Big Bang nucleosynthesis, is responsible for the elemental composition of the universe as we observe it today. In the subsequent hundreds of thousands of years, the universe entered a phase dominated by radiation, during which photons of light were scattered by free electrons. The release of these photons marked the formation of the cosmic microwave background radiation, which now pervades the entire universe and serves as a snapshot of the universe when it was just 380,000 years old. The universe continued to evolve over billions of years, with gravity playing a crucial role in the formation of structures such as galaxies, clusters of galaxies, and cosmic filaments. Over time, stars formed from clouds of gas and dust, initiating processes of nuclear fusion that release energy and create heavier elements through stellar nucleosynthesis. The story of cosmic evolution is not without its challenges and mysteries. While the Big Bang theory provides a comprehensive framework for understanding the universe's expansion and early development, it does not address certain fundamental questions. For instance, what existed before the Big Bang? Was there a time when the laws of physics, as we know them, did not apply? These questions push the boundaries of our current understanding and motivate ongoing research in theoretical physics and cosmology. One intriguing possibility is that our universe is just one of many in a vast multiverse, where each universe may have its own distinct physical laws and constants. The concept of the multiverse arises from theories such as string theory and inflationary cosmology, which suggest that our universe could be one bubble among many in a larger cosmic landscape. String theory, for example, proposes that fundamental particles are not point-like objects but rather tiny, vibrating strings of energy. These strings exist in multiple dimensions beyond the familiar four dimensions of space and time. String theory seeks to unify all known forces of nature, including gravity, within a single theoretical framework, a goal that has yet to be conclusively achieved but remains a focus of intense research. Inflationary cosmology, on the other hand, posits that the rapid expansion of the universe during the inflationary epoch may have led to the creation of multiple pocket universes within a larger inflating space. Each pocket universe could have different physical properties, leading to a diversity of universes within the multiverse. The idea of a multiverse raises profound questions about the nature of existence and the origin of physical laws. If true, it suggests that our universe is just one possible outcome among an infinite array of possibilities. Moreover, it challenges the traditional notion of a unique and singular cosmic beginning, inviting us to reconsider our place in the larger scheme of reality. Beyond the theoretical realm, observational astronomy continues to provide new insights into the structure and history of the universe. Advanced telescopes and observatories, such as the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope, JWST, have enabled astronomers to study distant galaxies, map the distribution of dark matter, and observe the afterglow of the Big Bang with unprecedented clarity. The study of dark matter and dark energy, which together make up about 95% of the universe's total energy density, remains one of the most pressing challenges in modern cosmology. Dark matter, which does not emit, absorb, or reflect light, is inferred from its gravitational effects on visible matter and light. Its presence is believed to play a crucial role in the formation and evolution of galaxies and larger cosmic structures. Dark energy, on the other hand, is a mysterious form of energy that permeates all of space and is driving the accelerated expansion of the universe. Discovered in the late 1990s through observations of distant supernovae, dark energy poses a significant puzzle for physicists and cosmologists alike. Its nature and origin remain poorly understood, leading to various hypotheses ranging from modifications of Einstein's theory of gravity to exotic forms of vacuum energy. The study of cosmic microwave background radiation, CMB, has provided a wealth of information about the early universe. Tiny variations in the temperature and polarization of the CMB, observed by satellites such as the Planck spacecraft, offer clues about the distribution of matter and energy shortly after the Big Bang. These fluctuations are believed to be the seeds from which galaxies and large-scale structure formed over billions of years.